I welcome you to the second day session. Basically, in today's session, we go through the DS-PAW software, where we learn about the material properties, like for the electronic properties, optical properties, molecular dynamics, NEB method, and other tools also in the DS-PAW software. And we also go through the Device Studio GUI, like other tool option, like how to measure the distance and change the length also. Let's start. First, we talk about the challenges in the material science. After that, we talk about like DFT revolution, and we go through the DS-PAW introduction, where we learn about the DS-PAW based on which theorem and like their core features and capabilities. And after that, we see how it works the DS-PAW software and their practical application also, and some advanced topics like parallelization and other parameters also, and their learning resources and other steps also for the DS-PAW softwares. When we talk about like in the material science, the first problem come with the like exponential scaling problem in the material science, and like experimental it will take some time and money and cost both. And like you can see a computational complexity crisis also before the computational method like first principle and other method also like Hartree Fock, and their industry affected also. You can see the pharmaceutical, semiconductor, and catalysis also. When you talk about like critical challenges, you can see here the predicting electronic structure like band structure, density of state, charge distribution, and other parameters also. Same way for the bonding and reactions, material by design, and like catalytic mechanism, calculating optical and magnetic properties, and balancing accuracy and cost also. Let's talk about like DFT revolution. When you talk about the reactive revolution, first we go through the Kohn theorems where we find the ground state electron density, determine the external potential and other properties also, and talk about like ground state energy and density also. After that, we introduce Kohn's sum equation, and where we find the non-interacting system with the same density, and where key achievement like the system size and cost reduction and versatility, no empirical parameters in the DS4 software. Like if you see the step here, first we initialize the density. After that, we build the potential and we solve the Kohn-Sum equation and update density. Maximum DFT-based software works like this. First, we initialize density and build potential. After that, we solve the equation and update density and check convergence. Again, it will follow the loop after, before the convergence. And you can see the convergence steps also like linear mixing you can use, Poulet, Broyden mixing you can use in the every software like Nanodecal, Rescue, and DS4 software also.
Hello,
Yes.
sir. This equation mentioned the exchange correlation. If you just go back to the previous slide.
Yes, sir.
Yeah, in the build potential, this exchange correlation, how do you calculate the exchange correlation?
Basically, in our software, we pre-written these things like for the exchange collision, like for the LDA, GGA, PW, and according to that, we choose the pseudo potential also. Like for the nanodical rescue, we use the norm conserving pseudo potential, and like for the DS4 software, we use plain augmented wave pseudo potentials to for the orbital electron density and other parameters.
But as per my information is concerned, so how do you make the means like the approximate guess so that you can get the uh not exact but it's close to the exact properties.
Yes, sir. In basically, nanodical based on like non-consuming pseudo potentials, and we use according to the exchange correlation function. Like if we choose the LDA, according to the LDA method, we choose the pseudo potential, like on the Mortius ONCB method and other parameters also.
Okay, thank you.
Basically, DS4 used on the first principal calculation software, and it is developed by HJW Software, the China-based company. And They offer for the first principle software, and it basis on Plane-Wave basis set for pseudo potential and ConSam DFT software. Their target application like insulators, biomedicine, semiconductor, battery material, and 2D materials also. You can see it also integrated with the GUI, Device Studio GUI, where you can easily create your material file and simulate also at a single platform. And you can use for like DS-PAW tool using Python for the post processing also. Like here you can see DS-PAW tool for the post processing also. Here you can see the pseudo potential comparison using WASP, Rescue, and DS-PAW for the pseudo potential comparison, and where you use the projector augmented wave method, and where supported functional you can see LDA, hybrid, GGA, and Wonderwall and TFT also, and you can use for the like magnetic properties, general purpose accuracy, transition metal with the semi-core states also. If you talk about like a core feature and capabilities of a DSP software, like here you can see the functional also LDA, GJ you can use, hybrid function you can use like HS06, and Havard term you can include, and van der Waal interaction you can include in the exchange collision function also. Electronic structure you can find DOS with the total DOS, projected DOS, band structure you can do, band unfolding in DSP you can do. You can find charge density, ELF you can do, better charge analysis you can do in the DS4 software. Structure evolution through the conjugate gradient method. You can see at the geometry optimization through the CG, NEB transition state you can do, AIMD with the NBT and NPT also. And you can do the cell optimization also. And in the magnetic property, you can include collinear spin also, non-collinear spin, and spin orbit interaction you can also include. Same way for the linear response, you can find elastic constant, dielectric tensor, piezoelectric tensor, phonon you can find. And in optical property, you can find refractive index, reflectivity, absorption coefficient, and dielectric function also. And if you talk about like their additional features, you can include external electric
Hello.
field. Yes, sir.
Sir, this for the van der Waal complex.
Yes, sir.
So, you mentioned this DFT. What is this DFT decorrection?
Sir, in, basically, Havard we can use for the rare earth element for the where d orbital interaction included, d and f orbital interaction included.
Okay. So, in that case, how do you calculate the exchange correlation for this?
Sir, you have to give the value in the U parameters and D parameters from the research papers and other
Okay.
documentation.
Okay. So, the parameters, what you mentioned, the D parameters and the F parameters that are existed previously, isn't it?
Yes, sir.
Okay. And what about this like van der Waal complexes for like long range interaction?
I didn't get, sir. Can you explain?
In case of the van der Waal complexes
Hmm.
for inner exchange correlation, where for the long range interaction there are two different kinds of interaction, such as like the short range interaction as well as the long
Like
range.
you can use for the layer materials also, molecular crystals, and like for the heterostructure. And when you work for the gas sensing devices like absorption strength, layer
Mhm.
spacing, this type of you can use for the Wonder Wall.
Okay, okay,
And
okay.
you can use like DFT D2 and DFT D3, this type of
Hmm.
function you can use.
Okay, okay.
And PS4 integrate with the Device Studio GUI, where you can easily create your crystal surface molecule with few clicks. And after that, you can set the parameters also. After that, for post processing, you can use the DS for Python tool for the post processing, like for the band structure, projected band structure, and other parameters also to see the value. And you can see the parameter organization also. First, you have to give the parameters, calculator parameters, SCF control, geometry optimization, and output control also. And it also support the pseudo potential for the uh, WASP also and other tool also like POP, PSP, GRB library. It also supported. You can see here the pseudo potential support. It also support the pseudo potential of VAS also. When you talk about like how to create a DS-PAW input file, first you have to create your crystal structure. After that, you have to choose the pseudo potential according to the your need, like LDA, GGA, and other methods also. After that, you can choose the K point and cutoff value and run the SCF and analyze other parameters also, like band structure, DOS, projected DOS, and like first to include like a beginner calculation, first you have to generate the SCF, and like you can do the relaxation also. After that, you can find the analysis for the bands, DOS, and other parameters also. You can see the application area in the DS4 software. You can use for the semiconductor material, 2D material, and battery material. You can do find the battery related parameters and catalysis, like solvation model also included in the DS4 software. You can include magnetic material also, and you can use for the 2D materials, and phonon and thermal property you can also find for any materials. And like you can use for the AIMD also, like it also include AIMD option, and NEB transition state you can find, and Havardu term also you can include. Spin orbit coupling also include, like SOI, same for the rescue and nanodecay, and you can include also solvation model if you want. And in the upcoming last week of the month, we also organized one workshop for the solar cell related. One of the client from the IIT Roorkee, they organized solar cell related software. They published paper using our software, using SetFOS, and it on 30th April, 3 to 5 p.m. from the IIT Roorkee. Please join this session also. Let's move to the Device Studio and create some example related to the DS-PAW software and simulate some example also. I hope everyone downloaded the Device Studio. Open the Device Studio software. Click on offline and create a new project. In earlier session, we basically go through the Device Studio GUI. Again, I repeat, this is a Device Studio GUI where you can create your material also, import your material file, and you can create a device structure, crystal structure, surface, and simulate also using the simulator option. In the simulator option, you can see multiple simulator like NanoDecal, NanoScheme, Rescue, BDF, MoMap, and other parameters. For your license, you can use only 4 tools: NanoDecal. NanoDecal is used for the material plus device both. Nano scheme is based on tight binding method. Rescue is used for the material, like based on density functional theory and density functional perturbation theory, where you can find Raman properties, optical properties, phonon density of state, band structure, Mulliken, and other parameters also. And you can also use the DS-PAW software. In today's session, basically we go through the DS-PAW, where you learn about the structure optimization, electronic structure, NEV method also, AIMD, you can find vibration method also. At the top section, you can see the menu bar in the file option. So the file option, you can create your new project, open your existing project, you can save your current project, and from the new option, you can create your device, crystal, and molecule also. From the import, you can import your material file through the local database and through the online database. And you can export your material also in the CIF and other format. Same in the build tab. So the build tab, you can create your molecular structure, 2D molecular structure. You can create a device, interface builder, like cat to atomic to for the interface between two or more material file, and same for the crystal, and redefine crystal to create a supercell structures. And to create a nanoribbon structure, you can use graphene nanoribbon, nanotube. Same for the nanotube, nanowire, and disorder graphene like structures. Go to the file option to import any material file. Click on import and click on import local. Here you can see the Device Studio offer wide range of material database like 3D material, organic material, 0D material, 1D material, and 2D materials. If you go inside the 3D material, you can see the semiconductor, insulator, layer material, magnetic material, metal oxide, conductor you can also see. Same for the organic materials. You can see the crystal and molecules. Inside you can see the some molecule present also. Please mute yourself. Bilal, please mute yourself.
One.
You can see the 0D material also. And in 1D material, you can see the nanotube structure with different crawl vectors. 2D material, you can see here novelty materials, graphene structures. Go to the 3D material option. And from the 3D material, go to the layer material and choose MOF2. And you can see here, Device Studio offer wide range of material format also. Apart from HZW, you can import in XYZ format, CIF format, postcard format, AIMD format, molecule, and PDB format also. Let's import here MOS2. Here you can see the MOS2 structure. And in the property section, you can see the coordinate of the MOS2 structure and their total number of atom, 9. Total area of lattice you can see here, and the chemical formula of MOS2 you can see here. Let's delete some atoms from here. Left click of the mouse and delete. At the top section, you can see toolbar enables. Here you can see the delete option. Click on this to delete atoms.
Please.
Bilal, please mute yourself. I hope everyone completed up to here. Please confirm.
Yes, sir.
To move to the center, left click of the mouse and click on the center. Go to the simulator option to optimize structure. Click on the DS-PAW software, and there is option for the structure optimization. Click on this. I'm audible?
Yes, yes, yes. Now it is audible.
Okay. Again, I repeat. First, go to the file option, import, import local from the 3D material, layer material, choose MOS2 and import. Click on open. And after that, left click of the mouse and delete. And left click of the mouse, select all these atoms. And there is option for the delete atom. Click on this. Again, select these atoms and click on the center option. To optimize this structure, go to the simulator option. There is option for the DS-PAW software. Click on this DS-PAW and there is option for the structure optimization. Click on this and here you can see the relaxation tab. In the relaxation tab, you can see the number of steps and you can see the algorithm also. According to your material file, you can choose also like conjugate gradient, cosine Newton, and molecular dynamics. Apart from that, you can see the constants. If someone want to fix their position of atom, you can also do. By clicking on this, you can see the position constants. You can fix also in the particular direction, X and Y, Z, you can see here for particular atom. Someone in the previous session asked about these things for the relaxation. Same for the lattice also. You can fix the atom in lattice also for in particular direction also, like for fix in Y direction, Z direction. For a time being, uncheck these both box. And in the relaxation convergence, you can see here, it shows the by default. You can converge in the form of energy also and through the force also. Click on the force. And here you can see the degree of freedom for the relax only atom position. You can relax all things like volume also, lattice volume also, atom position also, and their lattice structure also. So the relax all option. You can relax only the cell volume also, and you can include relax atom position and cell shape also. For a time being, only relax atom position. In the solver setting, you can see the K point sampling like N1, N2, N3. And you can see the gamma center and pack methods. Same for the smearing type like Gaussian and other parameters also. Here you can see the electronic loop and convergence also for the SCF included. And here you can see the cutoff factor and symmetry option also. For up to now, you can check the input file also by clicking on this input.in. Go to the physical setting. In the physical setting, you can see the spin type. You can include also spin like collinear spin, non-collinear. And you can set the spin also using this. You can also include spin orbit interaction if you want. Let's go for the none. And you can also include like Wonder Walls by clicking on this. You can choose the method here like DFT D2, DFT D3 also. You can also include hybrid function like if you want for the HSLU6, you can also include using the hybrid functional like HSLU6 03 B3LYP also you can include. Same for the Coulomb interaction. And here you can see the element specific setting like pseudo potential regions. If you go to the advanced tab, you can also include if you want background charges, dipole correction, solvation model, and hybrid factor also. For a time being, you can check the input file also like the task, system structure, functional, and other parameters also. Click on OK and click on generate file. In the left section in the project file here, you can see it created a folder, MOS2 folder, then DS-PAW folder. In the DS-PAW folder, you can see the two input file, relax.input and structure.as. Structure.as basically include the Cartesian coordinates of your MOS2 structure. Right click to see the, here you can see here, lattice and Cartesian coordinates. Click on relax.input file, and here you can see the script also. It divided basically in four tasks. Like you can see a task is equal to relax, and here you can see system structure. Like it take the data from structure.as. From here, it take the Cartesian coordinates and lattice parameters. And after that, you can choose the like functional PB method, and spin we go for the none. Symmetry, you can see the true here option, and same for the K point here, cutoff factor, relax maximum step you can see here, and the method you can see conjugate gradient, and you can see the relax dot freedom. It means we only will relax atom position, not all atom, all basically cell volume, lattice, and atom position also. We only go for the atom position relaxation. If you want to edit something, you can change in the script also. After changing, you can save and click on run option. It will create a log file with the name ds-paw.log file, where you can see the loop method also and other parameters function. For a time being, let's measure the distance between these two atoms also. Here you can see after the convert to device option, there is option for the distance. Click on this. Click on one atom, then control button, and click on another atom. Now you can see the distance also. Do for the same also here. I hope everyone completed up to here. Please confirm. If anyone have doubt, please ask. I hope everyone created the relax.input file also and calculate the distance also. You can write in the chat box also. Let me repeat these things again. To measure the distance, there is option for the distance option here. You can see here. Click on this. Click on this atom, and after that, to select any other atom, you have to click on control, then select another atom. Same for the other two atoms also, and these two atoms also. And you can see the process also. Relax.input in job manager, you can see in running condition. It's not completed yet. For the time being, you can see the build option. In the build option, there is option for the symmetry. You can see symmetry option. If you click on this, you can see the property of this crystal also, like their periodicity, name, space group, origin option, crystal class, and crystal system. You can also see like the hexagonal, and you can see the operator also going through the symmetry option. Build, then symmetry. Again, to create like a surface and slab, you have to go to the build option, and there is option for the surface and slab. Click on this, and according to the mirror indices, you can choose. And you can also include vacuum if you want, and you can include also slab. In this way, you can create also surface and slab option using the build, and page option for the surface and slab. You can choose any material file from the here, three dot, you can choose, and you can create also surface and slab also using these build option tools. Again, in the build tab, there is option for the disorder graphene like structure. If you want to create a disorder graphene like structure, from the here site A, you can see the site A. By default, carbon is selected for 4, and side B also you can see by default carbon is selected. If you click on this, you can change also with any other element. Same for the side B, and you can assign the bond length here. And here you can see the supercell. You can change also if you want. Click on preview, and you can create a disorder graphene like structure also. And click on build. Here you can see relax.input file completed. You can see the raw file also for a total charge, and you can see the 2D module in along XY direction, Y and Z direction, and you can see in the statoscopic display also. And you can see in the 1D in XY plane, YZ plane, and XZ plane. You can export in the image format, and you can change also the title and other parameters through this tool option. And there is option for the relax.json file where you can see the dump file also. And if the you can see the animation through the by play animation aspect. If the number of frame are greater, you can see in the better way. In the AIMD, you can see the process also, like how the relax your atom and move the atom position also. And to import your latest structure, relax structure, right click, open containing folder. Here you can see the latest structure.as file. Let's import this. There is option you can directly import from here also. Import local material. Go to the project path. And here you can see the latest structure.as file. Click on this and click on open. And now you can measure also the distance also. And you can see in the latest structure there lattice area and other parameters to atomic position and Cartesian coordinate also to compare also. And in the log file, you can see the lattice vector, their coordinate type, and K point. Here you can see the reduced K point size. And after that, you can see the loop also, and the iteration number of iteration you can see, loop 3, and other parameters also, like the pressure, volume, and total relaxation time. You can see the small difference in the bond length and the distance you can see for this structure. And this is a relaxed structure. You can see 2.415 and 3.15. And the initial structure you can see here 2.41, and here you can see 3.17. And like to find the electronic properties of any material file, again let's import any material from the material database. Go to the file, click on import, import local, and from the 3D material, semiconductor, let's import the silicon material and click on open. I hope everyone completed up to here for the relaxation of MOS2 also.
Yes, sir.
Okay. Now let's find the electronic properties for the silicon material. Go to the simulator option, and there is option for the DS-PAW. In the DS-PAW, you can see the electronic structure. Click on this, and you can see the first step, SCF, self-consistent field calculation. To find the basic parameter, first you have to create the SCF file. Click on this. If you double click, it will open here, and you can see the property also. Like click on this, and you can use this arrow button also. And here in the SCF step, you can include the wave function also, charge density also, and click on the solver setting. In the solver setting, you can see the K point sampling, cutoff factors, and you can see the type also like Gaussian, and you can also include the electronic loop for the mixing type for the SCF step, and convergence also. Same for the physical settings also. You can see the spin type none. If you want go for this like collinear general spin, it will take some time. For a time being, let's go for the none. And you can see the input file also by clicking on this. And you can see the structure file also for your silicon structure. You can see the total number of atom, lattice, and their Cartesian coordinates, and click on generate file. Here you can see the silicon crystal and their folder also, DS-PAW folder. In DS-PAW folder, you can see SCF input file and structure.as file. Right click and click on open with to see the script. The first thing you can see the task SCF, self-consistent field calculation, system.structure, where it will take the lattice parameters and their Cartesian coordinates from the structure.as file. And functional, you can see we choose the PB method. After that, we go for the none, collinear spin, not any spin properties here, and symmetry is true. K sampling, you can see K point here, you can see cutoff factor, and the mix type you can see here, Poole method. Click on save, and let's run this process. Right click, click on run. and it will simulate your SCF input file. You can see in the running condition, it also completed. You can see the raw file also for the SCF. You can change the ISO surface also by doing this, and you can change the color also. 2D and 1D also. And like to find the band structure property, DOS properties, go to the simulator.
Oh, sir, hello, sir.
Yes, sir.
Sir, sorry for the interrupt. Sir, I have an question. So, uh, yesterday I have mailed in your official website for buying the license of this software.
Yes, sir.
Sir, till now I didn't get any mail from your side. So,
Okay, sir. Let me discuss with my team, and then I will let you know, sir.
okay, okay. Thank you, sir. Thank you.
Okay, sir. Again, go to the DS-PAW option, and in electronic structure, you can see other parameter: density of state, band structure, potential, ELF, partial charge, Warnier function. Click on density of state. You can use arrow button, or by double click you can also include. Double click, you can see the SCF. Then click on density of state, not SCF. Click on density of state. If you click on the density of state, you can see the parameter related to that. K point sampling, energy range you can see here. Let's decrease the energy range and go for the 5 -5 to 5. And you can see the energy shift and type. And if you want for the projected, you can also click on true for the projected band structure. For a timing, let's go for the normal band structure. Sorry, normal density of state. Same for the band structure, double click. And to see the property for the band structure, click on the band structure. Here you can see the high K point path, like symmetry K point. Click on the path. You can see the belowing zone path. You can change the value also. You can delete, move up and down according to your need. And click on apply. And you can see the type, the width, and projected band structure. You can also do band unfolding. You can do. For time being, we can go for the normal band structure. After that, we go for the band unfolding and projected band structure also. Click on generate file. It asking for the if you want to use the SCF input file, old one. Yes, click on OK. And you can see here it created DOS.input file and band.input file. Right click, open with. You can see the script of density of state, and same for the band.input file. Again, I repeat, to create the input file for the DOS and band structure.input file, go to the simulator, DS-PAW, electronic structure, click on density of state, click on density of state here. If you see here calculation selected, click on density of state, check the parameter. You can, if you want to from -3 to 3, you can change resolution, you can change, and K point also. Same for the band structure. Click on only band structure, and you can see the K point there below in zone path also. After it, click on generate file. It asking for if you want to use old one SCF input file, click on OK, and then generate the DOS.input file and band.input file. Right click and click on run. Same for the band structure, band.input file, click on run. In the job manager, you can see DOS.input file in running condition and band.input file in queue condition. For the timing, I'll show the documentation also for these softwares. Type the HZW AI. The first website, click on this hjw.ai and click on the product. You can see the product list also, like Device Studio, Alchemist. Alchemist basically used for the chemical drawing, like same way for the chem draw. And you can see the quantum chemistry software also, BDF MOMAP. And here you can see the density functional theory software, DS-PAW and Rescue. In the DS-PAW software, you can see the main functions here: exchange collision function, electronic structure, structure evolution, magnetic properties, linear response theory, optical properties. And in more function, you can include external electric field, solvation, and potential bias also. You can see the software highlights also, and the application case also, like electronic structure analysis, absorption energy, reaction energy, charge analysis you can do, like someone asking for the charge analysis, differential charge density. You can do here also differential charge density, phonon spectrum, molecular dynamic simulation also. And to see the documentation, you can click on user manual to download the PDF file. And for the website, click on this website to see in the Chrome. For timing, I'll show the documentation also directly here. You can see the DS-PAW manual. Like this, you can find the band structure, projected band structure, DOS, PDOS. You can also find this type of PDOS. Potential you can find, band structure, and you can see the Van der Waal tutorials also here, Van der Waal correction calculation, optical properties, frequency calculation you can see. And you can see here the reaction coordinate also, like using the NEB method. I'll show the NEB. You can see the DS-PAW and the number of ionic steps. So for the spin orbit coupling, you have to look into the, like if you go for the rescue nanoscale, nanodecale and in DS-PAW, you have to see the raw file of the SCF file. Here you can see generate the scf.h5 also to see the spin orbit coupling data also. For the this you can see the manual also. Like for you can see the spin orbit coupling calculation, sir. You can go through this tutorial and find parameters related to the spin orbit coupling also. You can see band structure and DOS completed. Let's see the DOS file first. You can see the density of state for the silicon structure. You can see the DOS file. You can also export in the PNG format and text format also. You can see PNG and text format. Same for the band structure. Here you can see the band structure also. I hope everyone completed up to here. Please confirm so that we can proceed further for the projected band structure and projected density of state also. You can write in the chat box also. If someone facing an issue related to the band and DOS, please ask. I hope everyone get their result also, like for the DOS and band structure. Please confirm. If someone facing any issue, please let me know so that we can go hands on hands. You can write in the chat box also.
How heavy is this calculations? Like, can it be run in our laptop itself?
Yeah, what sir?
How heavy is the calculation, no, sir? Like, can we run it in the laptop itself or not?
Yes, sir. You can run in the normal system also. But if you go for the like 100 plus 200 plus atom, it will take some time.
Like, what's the configuration that you are running, sir, currently? Your
I
laptop
sir,
configuration.
i5 and 16 GB RAM.
Okay, so this unit cell can be run in that kind of system, right?
Yes, sir. No, easily you can run.
But if we create a supercell and all during that time, can it be run in the laptop itself?
Yes, sir. But it will take some time. Like if you go for the 50 plus 100 plus atoms, it will take some time to compute.
It won't create any problem with the laptop later on.
No, sir. No, sir. No, sir.
Oh.
And if in between it will pause, you can also resume also at the particular steps.
Okay,
Like
and
SCF, if SCF you stop at 5 steps, after that you can start from the 6th step.
can we publish the data that has been generated from this demo version or not?
Sir, I have to ask from my team, then I'll let you know, sir.
Yeah, like you are giving us license for 1 month, no? So if
Yes,
we
sir.
are running some good calculation during that time, are we allowed to publish with this license
Sir,
or not?
I have to discuss with my team, then I'll let you know, sir.
Okay, okay. So, and also the one which we have installed, I think there is no parallelization, right? It's just serial version. Only one core can be utilized.
No, sir. If you go for the like Linux system, you can run in the parallel also, and for Windows, you can use it basically use the thread parallelization, inbuilt thread parallelization.
Oh, we don't see any option, no? Like number of cores is only one for our
So
case.
basically, here you can see this option is only for the cloud. When you go for the cloud, it will open the cloud option here and to like load the slum file. Slum file is used for the cluster basis. Like I'll show you. Here you can see I configure my Linux system. So this there's option for the. You can also include any other system also by clicking on the new. You can include like give the IP address, their username and password, and you can create configure another system also, and you can directly connect from here.
So like currently we are like, is it offline? Can we disconnect the internet and run this
Yes, sir.
Device Studio?
Yes, sir. Yes, sir. This is offline license, not a network license.
Okay. So in offline we can't parallelize, right?
No, sir. Basically, here you can see like if you have a Linux system or other system where the number of core great, you can include also using this
No,
option.
in Windows itself, like I'm running in a Windows laptop only. I have 16 cores, but
Yeah, it easily works, sir, for the 100 plus
during
items.
during installation, do we need to do something or what?
No,
Like
sir. It inbuilt thread parallelization. No need to configure anything.
no, when I'm trying to run, no, there is no option for that one. Only
Like I'll show you in the. Let me give some time.
only
I'll say.
one. My computer is showing, no, there is no other option, and run parallel on one of 12, or it's 12 cores, one of 12 cores. It's only showing that one. There is no option for threading.
Like this.
So let's share my screen here.
No, sir. I'll share my screen. I'll show you.
Okay. Yeah.
Basically, this is a Linux system,
Okay.
and if I type DS-PAW, it's asking for the number of cores. If I give four here, and it's asking for the input file.
No, for Linux we can do. That's not a problem. I'm asking how to do that in Windows, no?
Yes, sir. In Linux, basically, it inbuilt.
Yeah, Linux, I know how to do the parallelization and all installation, but I want to know that in Windows, no, how to do that in Windows.
Basically, sir, in Windows, it inbuilt in the application for the thread parallelization. No need to configure externally.
It didn't show anything, no, when we installed yesterday.
What,
Now
sir?
there is no option for that one, for parallelization. Or maybe this demo license version is only for running in serial one only. Is there
Yes, sir.
anything like that?
Like if you want for the like you want to run in cluster, you can go for the cloud also.
Mhm. Not for the cluster here only. Oh, it's okay. You can carry on, sir. I'll discuss later on with you.
Okay, sir.
So,
I hope everyone completed up to here and got the DOS and band structure also. For the projected band structure and for the projected density of state, again go to the simulator. There is option for the DS-PAW, and in the DS-PAW electronic structure, click on density of state. Click on this density of state, and there is option for the projected. Give the option true, and same for the band structure. Give the option here. Sorry, band structure. Click on this, and here you can see the projected option. Click on true, and click on generate file. And it's asking for the use the old HCF input file. Click on yes. Okay. Again, run this dos.input file. Same band.input file. It will take some time. For a time being, I'll show the log file also. Here you can see the task type. Like here you can see the number of process here. In the Windows system, it will show one number of process 1 year also. And you can see the file name, atom symbol, atom number, and the structure also, lattice parameters. And you can see the parameters also, like the system electron, hybrid false, and other parameters also. And here you can see it's completed the SCF steps. Now it's calculating the DOS here. In the log file, you can see also task type density of state. And here you can see the calculating force and stress also. You can see the band gap value either, electron volt, and in Fermi energy, you can see in the electron volt, and conduction band minimum and valence band minimum, you can also see here. Here you can see for the PDOS, click on DOS.json file and click on show view. Here you can see the projected density of state, and there is option for the choosing the orbital also, like S, P, and D orbital. Like click on P orbital for the silicon first.
Sir, can
D
you please
orbital.
repeat the process for PDOS?
Yes, ma'am. Again, I repeat. Like to create the input file for the PDOS and P band structure, go to the simulator, DS-PAW, electronic structure, click on the density of state, double click. In the calculation selected, you can see the density of state. Click on this. It will show the parameter related to that. At the bottom section, you can see the projected option. In the projected option, it will show the false. Click on the true option. And same for the band structure also. Click on the band structure. And in calculation selected, click on band structure. and click on true. After that, generate file. And if you click on the generate file, click on OK, because it use the old SCF input file. You don't need to create the new SCF input file. Click on OK. And it will generate the band and DOS file. Run this file, and it will generate the projected band structure also. In this way, you can find the PDOS also, and you can export in the text and image format. You can import in the image format only here. And you can also edit also, if like title and any other things, you can change also, like X minimum, Y minimum, X maximum, Y maximum. And you can change the title also by edit panel. Same for the band structure also. Click on band.json file. And you can see for the S and P and D orbital also here. And like to do the post analysis, I show the post analysis option also. Here you can see the auxiliary tool guide. You have to install the DS-PAW, which using the Conda or pip install you can use for the installation of DS-PAW. And after that, you can give the input and you can generate multiple things. Like you can do post analysis. Like this way, you can do the volumetric data processing. And you can see this type of structures. Same for the grid size, like for the total electrostatic potentials. And you can import any material into another format using post-processing option. You can see the band data processing. Like this you can find. And you can also do the fad banding, fad band structure also in the DS-PAW. And you can do the post analysis like this and find only for the d orbital and s orbital also. Here you can see for px, py, and pz. And you can see the band unfolding option here also. Same for the total DOS here. Here you can see the band projected band structure. And like I show you the also other things. Right click on open containing folder. If you click here, you can see here some file here, band.h5 format. For the post processing, you have to use this h5 format. Like for the post processing, it also give the DS-PAW Python tool where you can integrate in the BS code and directly install using the pip and Conda also. And you can use post processing option where you can you do for the like particular p orbital, d orbital, like px, py, pz. Again, let's find the band unfolding for the silicon also. Again, go to the DS-PAW, electronic structure. In the band structure, double click, and in the calculation selected, you can see the band structure. And you can see a band structure unfolding option. Click on this and click on generate file. And it asking for the using the old one SCF input file. Click on OK. And again run the band.in file. In the chat box, someone asking for the difference between Nanodeckel and DS-PAW software. Basically, Nanodeckel is used for the material plus device port, and method are different. In the nanodical software, it is based on density function theory, non-equilibrium Keen function, and it uses the pseudo potential like non-conserving pseudo potential. And in the DS-PAW software, you can use for the plane wave, and where you can find the material based properties like electronic, optical, and other parameters also, like mechanical properties also you can find phonon, and you can use external electric field also, solvation model you can use. Like for the device, you have to move to the nanodical software for finding the device related parameters and properties. Here you can see band.input file completed. Click on this, click on show view, and it shows the normal band structure. Once you close this, it will open the band structure unfolding option. You can change the color map also. And you can change the X minimum, Y minimum also according to your need. In this way, you can do the band unfolding also to the DS-PAW software. I hope everyone completed up to here. Please confirm. Anyone have doubt related to the finding the parameters? Please ask. You can write in the chat box also.
Sir, after running the PDOS, how can we get the normal DOS structure?
Ma'am, first you have to you can create a multiple input file. Like here, I created only one input file. Like for the normal band structure, you can change the name also. Like go inside the folder and give the name here. Like PDOS, and same for the JSON file also. And now you can create a normal band structure, a normal DOS also.
Okay, every time I have to change the name.
What, ma'am?
Every time we have to change the name.
Yes, ma'am. First thing you can do, you can save the text file also and image format also.
Okay.
Okay.
But it will rename, no? previous file will not remain here.
Yes, ma'am. You have to rename, or you can want to first you have to generate the DOS input file. You can save also. After that, you can generate the PDOS also.
How can you please show?
Like first, create a normal DOS like this.
Okay.
Click on create file. Run this.
Okay.
Once it will complete, you can save your DOS file in image or text format. After that, you can again generate PDOS input file. In that way, you can save the result, both results.
Save from where?
I'll show you, ma'am. Like from the normal, this one, I show band.json file. There is option for the export image. You can export in image format also. And there is option for the text also. You can see here, export all data. You can export in text format also. First, do for the
First of
normal
all, we
and
have to save the first figure, then we have to run it again, and then
yes, ma'am.
the second one.
Yes,
Okay.
ma'am. And the second step is the renaming process.
Okay. Okay, thank you.
Again, go to the simulator, and there is option for the potential, and you can see the ELF also, partial charge you can find, and Warnier fund you can find. Like if you go for the potential, you can find local potential also, and electrostatic potential, and all potential you can find. Same for the ELF also.
सर बार्डर चार्ज एनालिसिस बताना
What's up?
बार्डर चार्ज एनालिसिस कैसे करेंगे
Okay, sir.
Weather charge analysis.
For the better charge analysis, when you created first SCF input file, that time you have to include like better charge analysis. You can see the option also here. Click on this, and after that you have to set the parameters also, and generate the file also. And it will show the better text file also. I'm showing the log file. You can see a better.txt file here. It will show the data related to that. During SCF input, you have to include the better charge analysis. Again, I repeat, simulator, DS-PAW, electronic structure. Once during the SCF, you have to include better charge analysis here. And after that, you can set the parameters and generate file. Once you run the SCF input file, it will generate the better.txt file.
okay thank you sir
And here you can see the potential also. Here you can see the type total electrostatic potential, total local potential. And you can see the graph also for the local potential and electrostatic potential. And you can see in the different plane also. And like for the finding optical properties and other parameters, again go to the DS-PAW. There is option for the vibration here. In vibration, you can see here phonon, frequency, elastic constant, epsilon. You can see. You can find the phonon by clicking on this. And in the phonon, you can see the method also, like finite displacement, linear response. You can choose according to your need. And you can change the supercell size also. You can also include the density of state, like for the for phonon density of state. And you can also include the thermal range also if you want. Same for the frequency and elastic constant also. You can see the solver settings, physical settings, and advanced. Same for the SCF like input file. Click on generate file. You can see it created different folder, like for the phonon, for the frequency, and for the elastic also. Run this input file to see the result. Let me show the previous project which I done earlier. Here you can see the structure. Basically, I do here first I import the silicon material After that, I relax the structure. And after that, I import the relaxed structure here. This one, latest structure. And I simulate multiple properties. Like this is the DS-PAW ES, it means electronic structure calculation, where you can see the multiple thing, potential you can see here. Two D potential, 1D, and total local potential. Band structure you can see here, and band unfolding for the silicon structure. Same for the DOS here.
Sir,
Yes, ma'am.
during this 1 month, if we face any problem related to running this software, can we
Yes, ma'am.
contact someone from your side?
Yes, ma'am. You can contact us. I'll share the number also in the chat box. If someone facing any issue in 1 month, you can coordinate with us. We can solve your issue also.
Oh, okay. Okay,
You can see in
that
the chat
70
box also.
that number.
Yes, ma'am. We share the number also, and we share the ID, Gmail ID also.
Okay.
I share the number and mail ID in the chat box. You can check the ELF file also here. Total ELF file.
Hello.
Yes, sir.
Sir, you mentioned like, you will provide the support, but like I remember I have written I have communicated with you regarding my this AG SNS.
I think so. I share the documentation related to the band doping effect, no?
That is the manual you have shared.
Yes, sir. And we also coordinate with the Google Meet link, but you will not join the Google Meet link also.
No. It was like, after 1 hour, I have mentioned, I have replied back to you.
Okay, sir. We'll coordinate with you regarding
Yeah,
the
sure.
doping list.
I hope in future, I think we will communicate it properly.
Okay, sir.
Yeah.
And here you can see the optical properties also.
So, what's the difference between the software and quantum ATK?
Ma'am, quantum decay used for the device and material, and same way, nanodecay is used for the device and material both, and same rescue is used for the material only, where you can use the multiple exchange correlation function also, and you can find Raman properties and other parameters. But the method are different. In the rescue, you can use density functional theory, density functional perturbation theory. You can also include the GPU computation also, and in the DS-PAW, it is based on Plane-Wave. If someone using WASP, it is a competitor of WASP for the DS-PAW software. They can use the pseudo potential of WASP also, and you can find material parameters also, like for the vibration and phonon and other parameters also, like optical, electronic structures, and other parameters also. In nanodical, you can use for the material and device both.
What is
They,
this nanoscheme and DS4? These softwares we can access from one platform.
yes,
I mean,
ma'am.
this from Device Studio.
Yes, ma'am. At
And
a
quantum
single.
ATK is different. No? I mean,
Yes,
that
ma'am.
is okay. That is an
Here it is.
individual.
Yes, ma'am. If someone working on the quantum chemistry, they can also go for the like BDF and MOMAP software. But in this license, it's not included. If someone working on the quantum chemistry, they can also coordinate with us for the BDF and MOMAP software. You can see in the simulator option also. The other simulator option also included, like BDF, MOMAP, and other parameter. And we offer the GY for the other software also,
What is on
like
a
for the
solar cell? You have to buy that SATFOS simulation software.
ma'am for solar cell.
Yes.
Yes, ma'am. If you are looking for the solar cell related, perovskite related, you have to move for the fluxing, where you can go for the set for software, law software. And in
So
at the
can we get
30th
that?
of April, at 30th of
Okay.
April, basically we have a session from the one of the client from IIT Roorkee. They're using the software from last 2 years, and they publish the paper also, and they will organize the workshop related to set for software. You can
Okay, can
join.
we have
And
one 30th of April?
what, ma'am?
Okay.
Basically, if you go for the like trial license in the Fluxing software, it will some limitation for the Fluxing software. You cannot fully utilize in the solar cell softwares. There are some limitations regarding the using the all modules. Here, ma'am, you are not audible clearly.
Yeah, how can we get the software set first? Means how much
Ma'am,
does cost?
ma'am, for the cost, we'll coordinate with you. You can share the details on this number or in this email ID in the chat box we'll give in.
Okay. Okay.
And here you can see the further optical properties for this silicon structure. You can see here dielectric function, absorption coefficient, optical conductivity, refractive index, reflectance, energy loss you can see here, and you can export in the PNG and other image format also. And you can also control like X minimum, X, Y maximum according to your need. And we also simulated like for the NEB also. I saw the NEB example. Like if someone working on the like NEB, finding the NEB parameters, first we have to select the initial structure and you have to select the final structure. After that, you have to use the method also, interpolation method, like linear, and the number of images you want, 8. And you can see the NEB parameters like calculation method and relaxation convergence, like using the energy or force. And if you want for the atom position and for the all, and you can check the constant also by giving here, like in particular direction. Same here. I show you the project also. Here you can see the NEB. We're finding the NEB structure. First, we created the structure, and after that, we add the one hydrogen atom here. And in the final structure, we move basically hydrogen structure at the bottom layer. And in the NEB method, we give the initial structure and the final structure. After that, we create the input file. Here you can see we go for the 9 images, and you can see the NEB input file here. After running, we get the NEB JSON file where you can see the reaction coordinates and convergence. You can see the convergence also for the structure index. And trajectory you can see here, like how the atom moves. Like to finding the NEB related parameters, you have to first give the initial structure and final structure, and after that you can simulate and you get the result like their reaction coordinates, convergence, and trajectory also. And you can do the post processing using the DS-PAW Python tool. And let me show the some example related to the nanodecal also for the device structure. Here you can see we created the graphene nano ribbon device structure here. And after that, we're finding the properties for the device. We're finding the density of state. You can see the here we included the spin properties also. It is for the spin up, and in spin type you can choose also spin down, and you can include both. And you can see the spin properties also, spin up and spin down properties. Same for the transmission also. You can see the spin type. Spin down, and you can check the both. And you can see the total electron density. Like for the spin up also and spin down. You can see in the 2D along y-axis also, and for the spin down and spin up also. Same Seebeck coefficient. You can see the chemical potential energy. You can find the mu value. Here you can see. And you can see the Seebeck and charge coefficient also. And you can find the chemical potential energy also at different temperatures, 100 Kelvin, 150 Kelvin. And you can see the thermoelectric. Wait. In this way, you can find for the device properties also. Like if I go to the nanodecal and go to the analysis, you can find the property for the left electrode. All these type of property you can find in nanodecal also, like density of state, effective potential, band structure, charge, Hessian, potential, trans channel, and other parameter you can also find. Like mechanical property you can find, force, stress, modulus, and other parameter. Thermoelectric properties you can find using the ZT method, and complex band structure you can find in the nanodecal. And here you can see the AIMD method using the DS-PAW. You can see the AIMD also. If you click on this, you can choose the NEB method and BT method, and you have to give the value here, and you have to assign the initial temperature. After that, you have to give the K point sampling and other accuracy cutoff factors, physical settings, where you can include the spin types also. After that, you have to click the generate file to create the SCF input file. And here you can see the aimd.input file. And you can see the task also, system structure, and other parameters also. And you can see the AIMD also, the steps, how the atom moves with the number of frame. And you can also export. And like for the post processing, I created some file also, open containing folder. And you can see here, we created some Python file for the post processing. After that, we get some the result also. Here you can see for the kinetic energy and for the temperature also. In this way, you can create AIMD also using the DS-PAW software. Someone asking for the IB graph, you can do IB graph through the Nanotechnology software, but for the to show the graph, you have to move to the MATLAB to see the graph related to that. You can do the Python also and MATLAB script also for the see the graph. Through the DS-PAW software, you can use the electrical conductivity also, and through the Nanotechnology also you can do. In phonon property, you can also include the thermal properties also. If anyone have doubt, please ask. And for the documentation, you can move to the website hjw.ai, where you can see the multiple product list, and you can move to the DS-PAW, and you can see the manual also. In the WhatsApp group, we will share that. What, ma'am?
Okay. Yeah, so can you please show me the how you can create rider or rider?
Ma'am, you are not clearly audible.
Yeah, can you please show me the how to create to rider or rider structure?
Ma'am, can you write in the chat box?
Yeah,
Your
sure.
query into the chat box.
Hello, sir. Hello.
Yes, sir.
Uh, uh, can I know what is the difference between the electronic structure obtained from the nanodical as well as from DSPA?
Band
The
structure, sir.
optimized electronic structure. What is the difference? That means you can say the Plane-Wave method, which is what in the DSPA.
Basically,
Is it
sir, it totally sir, based on the pseudo potential we taken. In nanodeckel, we will be taking choosing the non-conforming pseudo potential,
yeah,
and in the DS-PAW software, we take the pseudo potential based on the PAW method, projected or augmented method basis set we're choosing.
Plane-Wave method, Plane-Wave argument.
Yeah, Plane-Wave method.
Yeah. So, what is the difference of the electronic structure, optimized electronic structure, whether it is what more advanced or electronic structure, that means more accurate, or
Sir, it totally depends on the researcher, which method they are using for their research.
Mhm.
Every method have a pro and cons also, sir.
Yeah, obviously. So, but actually we are using that canonical electronic structure, but optimized electronic structure previously. But
Yes,
in
sir.
what way the DSPA is but advanced one, I think. But is it but having some specific difference you are
Yes, sir.
having
In
that?
the DS-PAW, you can include like a DFT plus U and DFT plus D also, and you can include the
Harvard model.
Wonder, yeah, Hubbard
Harvard
model,
model.
and yes, sir. And
Hmm.
they include also Wonder Wall interaction also you can do. You can also include the background charges if you want, like the background charges, solvation model you can include, hybrid factor. These type of parameter you can also include.
As well as a hybrid vector you can.
Yes, sir. Hybrid
Yeah,
factor you can also
yeah.
include.
Phase change parameter. Can you get this? What in the DSPA?
What's the?
Phase change. That means when by using the spin orbit coupling,
Yeah.
can you get the what phase change? Different structures phase change can be obtained from DSPA.
Sir, I have to check. Then I'll let you know, sir.
Oh yeah, yeah. I think what the DSPA is having what more advanced properties. So as you have explained, it is very nice. So I plan to what include the DSPA as also what with the nanodical as well as what rescue.
Yes, sir.
We
We'll
are
share the documentation also in
जो
the WhatsApp
yeah,
group.
yeah, yeah.
फोर में
So
उर्दू में पैसे
thank
मांग
you
रहे हैं,
very
वो भी
much.
सर बना
This
दिए,
is
वो भी तो 1500 ही मांग रहे हैं बिकॉज प्रॉपर्ली आई नहीं है उसमें
How to create MOS to tri-layer or bi-layer structure after optimization. Ma'am, you can create a by copying the layer structure or through the interface builder you can create.
Can you
Like
please
I'll
show
show you the
me
for the
can you please
graphene.
show me the process on how to copy or and include the layers? So from where you get this? From build.
Build and redefine crystal, ma'am. You can create a supercell structure. And again, if you want to create a same layer structure, there is option, select this, and there is option for the mirror. You can create mirror image of this material also. Like I'll show you. 0, 0. And click on apply. You can see here. You can also move by clicking on this.
Where is that mirror option?
Ma'am, I'll show you again.
Just move that.
This is the MOS2 structure.
Okay.
To redefine, go to the build option. There is option for the redefine crystal. Click on this. In the redefine crystal, you can create a supercell and click on preview. According to your need, you can create larger supercell. Click on build and left click of the mouse, drag a box and select all atom. And there is option for the mirror atom. Click on this and click on XY plane. And you can give the distance also, like 2 angstrom, and click on apply. Here you can see.
Okay.
In this way, you can create.
Okay. Thank you.
Someone asking for the how Device Studio differ from the Material Studio. Basically, Device Studio offer wide range for the GUI for the other tools also. Like you can in the simulator option you can see here. You can do for the devices also. You can do for the material also, and you can do for the quantum chemistry. And it offers the GUI for the other software also. Like you can see here, WASP, Quantum Espresso, Gaussian, and WCHM also you can see. And you can find like this type of virtual X-ray option, and you can find the XRD plot and diffraction data also. And through the build option, you can create multiple things like molecular structure, 2D molecular structure, converting of devices, bending of devices, redefine surface lab, nano ribbon, nano wire. And there's option at the last, you can see the convert file. Like if your material present in the another format, like in Python format, you can convert in the XYZ and other HZW format and XYZ format also. Like if someone working on the quantum ATK and their material file in the Python format, they directly import here and convert in the XYZ format directly here. Sir, a K point given by default, you have to choose according to the plane you have chosen, like X, Y, Y, Z, or the material, like 2D material, 3D material. According to that, you have to choose the K point. And in the upcoming version of Nanodical and Rescue software, we basically integrate these parameters because user don't need to input their parameter. It automatically select parameters like K points and cutoff factors and other parameters. Anyone else who have doubt, please ask. And you can refer to the our YouTube channel also, where we have created a multiple playlist for the these softwares, like for the Device Studio, Nanodical, and Solar Cell also. And you can join the upcoming workshop also, which we collaborated with the IIT Roorkee. They use the SET4 software for the solar cell simulations, and they publish the multiple paper using our tools. You can join this session also, who working on the solar cell, perovskite, tandem, OLED, and other parameters also. And we,
Hello, sir. What is the YouTube channel name, sir?
so I'll show you also. Impulse technology type. And here you can see the Impulse Technology YouTube channel. Where we created multiple playlists, like for the DS-PAW, Lao software, for the spin qubit devices, working on the superconducting circuit spin qubit devices, and project playlist also for the QTCAD. And you can see the Device Studio playlist, Rescue software, Nanodical software also. And if you have any doubt, you can also watch the video. And if you have doubt, please ask. We can coordinate with us also. We'll share the documentation for the spin orbit coupling also, sir. And we'll share the documentation for the Device Studio, Rescue, and DS-PAW on the WhatsApp group and the mail also. Anyone else who have doubt, please ask. You can use the 1 month license for the all 4 software for NanoScheme also, DS-PAW, Nanodical, and Rescue. And regarding if you are facing any issue, you can coordinate with us also. You can write mail or you can coordinate directly through the phone.